dealing with exponential growth and decay functions today, right at the start of class. Um, Talking about populations and depreciation of value and compound interest as your money grows over time. Y equals a times b to the x is the general formula that you can follow when dealing with exponential functions, at least exponential functions of common bases like base 2 or base 4 or base 10. Y stands for the final amount of whatever you're dealing with. A is the starting amount, whatever amount you started with. B is your growth or decay factor, where if B is greater than 1, you have growth, and if B is less than 1, you have decay. And an X or T could also be a T. Usually stands for time. Most of these things are amount over time type problems when they come up. Not always, but typically. So here's an example of exponential, well, let's see if it's growth or decay. Your experiment starts with 7,500 bacteria cells, and after 4 hours, there are 23,000 cells. So it's clearly growing over time. As time goes on, things get bigger, so we have growth. So our b value should be greater than 1. We're going to write an exponential function that can be used to model the population of y, the population in terms of y, after x hours. Well, here's what we know. We know that we had 7,500 was our starting amount. That's our a. 4 hours was our time. We'll call that x. And the final amount we had was 23,000. So we would have the equation, we're plugging into y equals a times b to the x. So it's 23,000 equals 7,500 times b, which we don't know, to the x of 4. We want to solve this for variable b to find what that actual growth rate is. Well, this is a typical polynomial type equation at this point, where the variable is the base, not the exponent. So we divide both sides by 7,500. 23,000 divided by 7,500 is 3.06. Now you want to be as precise with these numbers as you can. This is a very common mistake in this chapter, in this material. You want that number to be as precise as you can because it actually really makes a difference. So the next thing I'm going to do is take a fourth root of both sides. And when I take a fourth root, that undoes the fourth power. But when I do the fourth root in my calculator, I'm not going to type in the number 3.06 or even 3.06666. What I'm going to do is find a fourth root, and here's me doing a fourth root. A fourth root of, and second negative pulls up my previous answer. A fourth root of that number, and that's the most accurate way to do this. So the fourth root of my previous answer gets me 1.32333. Make sure that's right. 32333. When I write down the value, I can't go forever. But the more decimal points here you have, the more accurate you are. And depending on what you're doing, you might not need that many or that few decimal points. But now that we know what b is, we can have the equation y equals, our starting amount is still 7,500. Our base is now 1.323, I'll call it, to the x. This is now the equation that models the number of bacteria over time, where x is done in hours. And so I knew how much there was after 4 hours. How much is there after 12 hours? Well, I can just take this equation, I'm answering this question, and have y equals 7,500 times 1.323 to the 12th. But again, even though I wrote 1.323, in my calculator, I'm going to keep using this whole stored value, because it's the most accurate version. So I'll do 7,500 times my previous answer, my previous answer, second negative, gosh, Grant, second negative, to the 12th. And I get 216,302 cells. So you'll notice that even though the time that happened was more than 3 times, it was 3 times as long, the growth was way more than 3 times as much. Here, it just about tripled, maybe a little more than tripled, but from here to here, it was almost 10 times as much. So you can't use a linear way of solving these problems. The growth doesn't triple as time triples because it's exponential. It keeps growing faster and faster and faster over time because there's more bacteria producing more bacteria. So there's an example of populations. Most populations can be modeled in an exponential form, at least for a little period of time. Percents come up a lot with exponential growth or decay because you can gain or lose some percentage of something. And when you gain or lose some percentage of something, you follow this formula. But please understand, this 1 plus or minus r is just the same as the b we had before. It's the exact same formula, only you have to do a little bit of work to calculate whatever that b value is. Y is still the ending amount, a is still the starting amount, r is just the number 1, like it's literally 100%. And p is your percentage of change. It's really a rate. That's why we use r. It's kind of a percentage rate. It's usually an interest rate, actually. And x stands for time. So here's an example. A car is currently worth $13,000 and its value depreciates at a rate of 18% every year. Well, if you're losing 18% of something, it really means you're keeping 88% of it. So here's my a value, here's my r. This is the t or the x we're going to play with. I want to find y. I don't know the ending amount. But the ending amount is really going to be equal to my starting amount with 1 minus 0.18 to the 6. Losing 18% is the same as keeping 82%. That's the key here. When you multiply by something less than 1, like 0.82, your number gets smaller and smaller and smaller. And so each time that happens, you're decreasing. You have exponential decay here. Really what's happening, if you want to think about it this way, is you started with $13,000. Then after a year, you would have less. After you'd have $10,660. Well, then you're going to lose 18% of that. But since you have less money now to work with, you lose a smaller amount. Now you're down to 874. After the next year, you're down to 874. Well, another year passes, you're at 7167. I'm sorry, we've gone for another year. We've now gone 3 years. And in 3 years, you're down to this much. Well, then there's 4 years, there's 5 years, there's 6 years. After 6 years, your car is worth just under $4,000. So this came out to 3952.09. Because we really wanted to do it 6 times. And if we keep going, here's 7 years, 8 years, 9 years, 10 years, it keeps going down. But you'll note it keeps going down by less and less. Pretty soon it's barely decreasing. It went down by 11, went down by 9, went down by 8. But it's not going down by much because eventually it gets really, really close to 0, but never actually worth nothing because you've always got a car. You've always got some parts. It doesn't run. You've got some metal somewhere you can scrap. It has some value of some sort. And people always say, well, doesn't the value of cars go up? Sometimes. Very, very rare cases where a car is like an antique and collectible and taken really good care of can it go up. But in general, the values of cars depreciates very quickly. Okay, we're going to compare simple interest to compound interest. Now, simple interest isn't something we'll deal with in this class. Simple interest is where your money grows at a constant rate no matter how long it's growing. It's just the equation I equals PRT where P stands for your principal, which is your starting amount. Starting amount of money. R is your interest rate, T is time, usually in years. So like a car loan often does simple interest, where they say we're going to charge you, we loan you $8,000, we'll give you 12% interest. So that 12% interest is $960. Well, suppose that lasted for 2 years, you would do it twice, and you'd get $1920. But if it was 3 years or 4 years or 5 years, however long the loan was, they'd just keep doing 0.12 times 8,000 and calculate the interest from there. That's called simple interest, where it's just always the same amount. In this case, they'd be charging $960 for every year. Simple interest doesn't happen very often. It does in a lot of car loans, actually, but there's other cases where it doesn't. What's more common by a long shot is compound interest. Compound interest is when the interest you gain from one year affects the interest you gain the next year. So like if in 1 year you had $1,000 in the bank and you're getting 10% interest, well, the next year you'd have $1,100 in the bank. But the year after that, you would have a little bit more money to take interest on. So instead of getting another $100, oh, really? Well, I'll just go, meant it's a little bit off. Instead of getting another $100, you'd get $111. You got a little bit extra money because there was more money to take interest on, and that's compounding. It's compounding your interest. You're taking interest on the interest. So your rate of growth is always increasing. It's an exponential growth that grows faster and faster over time. We'll do two quick examples. So your bank account has $400 and is earning 3% interest compounded each year. Write a function relating the total money in the account to the number of years that have passed. Well, it's still going to be this type of function, only in this case, we use the principal. P is the principal, means starting amount of money, and because we're doing a percentage, we add it to 100. So if we're gaining 3%, our formula is really going to be y equals p times 1.03 to the x. And after 10 years, is this thing working yet? No, give me a second, I'll fix this. So we've got our formula, and now we're going to plug a 10 in for x, because 10 years is passing. So we have y equals, our starting amount was $400. Let's see what we get. We have $537.57. Well, let's do 20 years. From 0 to 10 years, the money went up $137. So we might expect it to go up $137 again for 20 years. But it actually goes up by substantially more. It went up by almost $190 because there was more money to take interest on each year. Each year there was a little bit more money from the previous year's interest, and that causes it to grow faster and faster, and that's the definition of exponential growth. One more example. I haven't actually given you a compound interest formula. It seems like it's really convoluted, but it's actually the same thing that we just did. Only now there's these two sneaky little n's in here. So here's how this usually works. Let's look at our last example where we had $400 and they were getting interest. But instead of compounding the interest, instead of calculating the interest once per year, we're going to do it once a month. Meaning we take that 3% interest that we had and we split it up into 12 different parts. Well, that splitting up of 12 different parts really changes it. Instead of getting 3% once, we get 0.25% 12 times. And that's what this is doing right here. This is taking your interest and splitting it up into a bunch of little pieces. N stands for the number of times you'll calculate your interest in a year. But since we're calculating it 12 more times, it happens a lot more often. So our interest rate kind of gets 12 times smaller, but the number of times we compound gets 12 times bigger, and these things have a small impact on what happens. So now our bank account has $400 and is earning 3% compounded monthly. Well, that's our N value. Our N value, because it's monthly, N is 12. If it was yearly, N would be 1. If it was daily, N would be 365. If it was weekly, N would be 52. Because it's monthly, N is 12. That's a very common way to do it. Well, so we have, this is our principal, this is our interest rate. We had our N is 12, so our function is y equals 400 times 1 plus 0.03 over 12 to the 12x. I just plugged the 12s in for the ends. Plugged 12 in here and here. Everything else stayed the same. So how much money is in the account after 10 years? So these are the last two amounts. Let's notice that. In the first case, we had 537. Now we'll do 400 times 1 plus 0.03 divided by 12 to the 12 times 10. Notice how I'm using parentheses on both of those things. Parentheses are really, really important here. The calculator will do 0.03 divided by 12 first. So I don't have to worry about putting this in parentheses, but the whole thing has to go in parentheses. Last time I got 537. This time we got 539. So it made us a little more than $2 extra, which isn't a ton, but if you can make $2 for not doing anything, you might as well. So this came out to 539.74. We just plugged a 10 in for x. Let's do it again, plugging in a 20, second enter, pulls up my previous equation. I'll go back and change this 10 to a 20. I type second enter to pop up the old equation, change 10 to 20. Now I got 728. It used to be 722, now it's 728. It doesn't make a big difference, but if you have enough money, like a lot of money, and you're doing it for a long period of time, it can actually add up to hundreds or maybe even thousands of dollars. So there's compound interest. It's interest taken on interest. It has exponential growth, just like how populations do. And that takes care of our video for today. Thank you.